Good morning, children. I hope you all have started preparing for Thursday's test of this chapter. Most of the syllabus is over. We just have a very small portion left, which I'll be completing it today. Okay. So, before that, I would like to say some corrections regarding Friday's homework. First of all, very few people have sent. I think only 10 of you had sent the homework. Children, these are very important questions and most of them are previous board questions. So please make sure you do them. Okay, these are the 3 questions that I sent in through attachment. Okay. Few of the common mistakes that you all have did. The first one was ice at -10 is heated till it becomes water at 50 degrees Celsius. So -10, 0 and 50. From -10 to 0, temperature will rise. As you apply heat, temperature rises and it will be in ice. At 0, melting will happen, and during melting, temperature remains constant. So you will have a flat line, a horizontal line like this. Then after that, again, once the entire thing has melted off, then again temperature will start rising, and they have told you to mark till 50 degrees Celsius, water at 50. So this should be your final point. So many of you had not written this on the graph: ice, melting, and water. You have to write the state. Okay, and these 3 temperatures, and then in the x-axis you will write time, in the y-axis you will write temperature in degree Celsius. And time, you need not write the numbers here, you just leave it like that. Now the second one was little hard. A naphthalene ball, a solid naphthalene ball, initially at 20 degrees Celsius, is heated till its liquid form reaches 100 degrees Celsius. Draw the heating curve. Melting point of naphthalene is 80 degrees Celsius. So draw the heating curve. So time, temperature. So we are starting from 20 degrees Celsius, melting point 80 till 100. Okay, so 20 degrees Celsius, then 80 degrees Celsius, then 100 degrees Celsius. Okay, now from 20 to 80, it will be solid naphthalene. Solid naphthalene. Okay, at 80, melting. Then from 80 to 100, you'll have liquid naphthalene. Many of you had not again written this form state of matter: solid naphthalene, melting, liquid naphthalene. Okay, marks are allotted for this also, the temperature and then the axis. Okay, the third one, what do you mean by the statement specific latent heat of fusion of wax is 1,46,000 joule per kg? Now again, many of you had written something, but you had not written all the points. Okay, so the answer will be, it means that amount of heat energy required to melt 1 kg of solid wax. Okay, heat energy required to melt 1 kg of solid wax. That's the first point. At its melting point, to liquid wax without change in temperature is 146,000 joule. This definition itself should have 3 points. Don't miss any of them. Amount of heat energy required to melt 1 kg. Because it is joule per kg, you will write 1 kg of solid wax. Because it's fusion, it is melting. Melting means solid to liquid. So it was a solid wax initially. So to melt 1 kg of solid wax, which is already at its melting point. You don't know its melting point, that's okay. You just write at its melting point. To liquid wax without change in temperature is 1,46,000 joules. Okay, so these 3 points have to be written. Many of you had not written without change in temperature, or many of you had not written at its melting point. One or some point was missing in this. That can okay, that is not correct. All 3 points have to be covered. And then in these questions, I told you to read few questions. I hope you all read through it. Now, these are how the questions come usually. Main thing is, during rise in temperature, kinetic energy increases. During change of phase, potential energy increases. Remember that. During change in temperature, kinetic energy increases. During change of phase, potential energy increases. Or during change of phase, kinetic energy will not increase, and during change in temperature, potential energy will not increase. So these kind of questions come very often. Same way, how does kinetic energy and potential energy change during change of phase at a constant temperature? Kinetic energy, no change. Potential energy increases. So these kind of questions also you can expect. Okay, now we'll go to the last part of this, that is natural consequences of high specific latent heat of fusion of ice. As I told you, ice has the highest specific latent heat of fusion, uh, that is 336 into 10 power 3 joule per kg. That means to melt 1 kg of ice, which is already at 0 degrees Celsius. Okay, I have ice, 1 kg of ice at 0 degrees Celsius. To melt this, how much heat energy required? 336,000 joule. 336,000 joules of heat energy is required to convert it to 1 kg of water at 0 degree Celsius. Okay, that is to melt 1 kg of ice at 0, you require 336,000 joules, which is a very high amount. Just imagine 1 kg of ice means a block, quite a big block like this, and to melt it you need this much joules of heat energy. Now this has some consequences, natural consequences. First is, snow on mountains does not melt all at once. So generally, you know that there are many rivers for which the source of water is melting of snow. Okay, and it happens through the year. It's not that, okay, in 1 or 2 months the entire ice cap melts. You know that it takes a long time, almost for 6 months in the year, summer months, snow keeps melting, and you keep that becomes the source of water for this source of um, water for these rivers. Okay, so in all these things, remember the first point will be ice has a high specific latent heat of fusion equal to 336,000 joule per kg. 1 mark for this. Okay, so because of that, what it is due to this fact, it changes to water slowly, in the sense ice needs so much heat to melt, so it will melt slowly. So if latent heat would have been high, would have been low, and all the snow would have melted in a short time, that would have led to floods in rivers and no water after that. How is it possible that through the year there is continuous source of water from the snow-capped mountains? It's because its specific latent heat is very high, it melts very slowly. Not all at once, it melts very slowly. So these are the two important points have to be written. Ice has a very high specific latent heat of fusion of ice, including the value, so it changes into water slowly. Second one, in cold countries, water in lakes and ponds does not freeze all at once. Same thing, in the sense the reverse of it. So water in lakes and ponds, suddenly, suppose it was in winters, one night it became 0 degrees Celsius. Okay, suddenly everything won't freeze. Okay, why? Again, this reason is that specific latent heat of fusion of ice is sufficiently high. If you're writing in joule per gram, write 336. Joule per kg means 336,000 also will be there. Okay, so first will be the value. So what happens? The water in lakes and ponds have to liberate large quantity of heat before freezing. So you should not forget this. During melting, it gives out heat. In the sense, no, it will take heat. Okay, if you want to convert 1 kg of ice to water, what you have to give? You have to provide heat. It will take heat. On the other hand, if 1 kg of water, so this is for melting. It will take heat from outside. But for freezing 1 kg of water, 1 kg of water to ice, it will give out heat. It has to give out heat. Okay, so that's why liberate means give out. So it has to give out so much heat energy before it freezes. So that's why it freezes very slowly. It doesn't freeze all at once. And you know this, a layer of ice is formed over the top surface, which becomes a poor conductor and prevents further loss of heat. This you've studied in last year. This property helps in survival of aquatic life. Okay, third one, drinks get cooled more quickly by adding pieces of ice rather than ice cold water. Okay, so you have two options. Okay, you have to cool a Coke bottle. Okay, so on a summer day, suppose you kept it outside and it was at say 35 degrees Celsius. Okay, you want to cool it quickly and you have two options. One is ice cold water. Ice cold water, that is also at 0 degrees Celsius. And then other one is ice at 0 degrees Celsius. So you have ice blocks at 0 degrees Celsius and another one ice cold water at 0 degrees Celsius. Which one will you prefer? In which will you put this? Into which will you put this so that it gets cooled quickly? Generally, we prefer ice at 0 degrees Celsius. Though temperature is the same. This is also water at 0. This is ice at 0. But still you prefer this because if you put it into ice, first the ice has to melt. And every gram of ice will take 336 joules of heat energy more from this. Here it is just change in temperature, but here there is a change of state involved, and every 1 gram of ice will require 336 joules of heat energy, which it will take from this cold drink, and the cold drink will get cooled quickly. Okay, that is the thing. 1 gram of ice takes this much of heat energy from the drink. So the drink gives out an additional 336 joules of heat energy than 1 gram of ice cold water. So that's why cooling is much faster. So this is the important point. Drink liberates or gives out an additional 336 joules of heat energy to 1 gram ice at 0 than 1 gram ice cold water. Because ice needs to melt, so it will give heat energy. Then the fourth one, ice is frozen. Ice in a frozen lake starts melting. Its surrounding becomes very cold. Okay, so lake is already frozen and then it starts melting now. Okay, one day the temperature has risen, so it starts melting. But even then, the surrounding becomes very cold. I think this you would have felt. I'll explain this first, then you'll understand. It is generally much cold after a hailstorm than during or before a hailstorm. So during winters, sometimes we also have hailstorms. You will always notice that after the hailstorm, the weather becomes very cold than during or before the hailstorm. Why? Hail is basically what? Small blocks of ice. So after the hailstorm is over, these blocks of ice will be collected here and there and they'll start melting. So to melt, they need heat. Okay. So the reason is that after the hailstorm, ice absorbs heat energy required for its melting from its surrounding. So the temperature falls further down and becomes very cold. And please, in both these explanations also, you have to write the first point will be because ice has a high specific latent heat of fusion, or because the specific latent heat of fusion of ice is very high, 336 joule per gram. Therefore, this will happen. When the hailstorm melts, every 1 gram of ice will give out, every 1 gram of ice to melt will take 336 joules of heat energy from the surrounding. So surrounding will become cold. Same thing will happen in this also. Okay. So these are the consequences of high specific latent heat of fusion of ice. Okay. Now for Thursday's test, you're not going to do the numericals. Okay, please don't do the numericals. Leave the numericals of B part. Only the theory of B part you will be doing. Okay, already you're clear with what to study. I need not explain it. Quickly I'll go through it. Start actual study, you start studying from this page only. First is heat capacity, definition, formula, unit. Then what do you mean by heat capacity of a vessel is this much. Then in specific heat capacity, again definition, formula, factors affecting. Okay, formula can be, you can write in this way or this way. Then factors affecting, SI unit of specific heat capacity, relationship between heat capacity and specific heat capacity, then difference between heat capacity and specific heat capacity. Then based on this, there can be reasoning questions. You have done the lot of questions in exercise based on this. Then based on calorimeter, there are 3 questions possible. I hope you remember what are they. Then you have consequences of high specific heat capacity of water. This is high specific latent heat of fusion of ice. Consequences of high specific latent heat of fusion of ice. This is high specific heat capacity of water. Be careful. Okay, again in this, the first point will be the same. Water has a very high specific heat capacity, but the way it applies, it's different. Water does not cool quickly. Here, water can extract more heat without much rise in temperature. These are the very important points. Make sure they are, the 1 mark is given for that. These ones which I have underlined, these are very, very important. Make sure you don't miss these points. Is it clear, children? And then the numericals of A part, we have done enough of practice, and B part only theory. Okay, I hope it's clear. So come prepared for test on Thursday. Please bring your test copies also. Thank you so much. All the best for your preparation.